Next up on our agenda is Jason Swope of NASA JPL presenting validation of flight software on the Qualcomm Snapdragon on the International Space Station. Jason, it's all yours.
Awesome, cool. Can you hear me?
We can hear you just fine.
Perfect. All right, so hello, I'm Jason, and yes, we're going to be going over our validation of flight software on the Snapdragon on the ISS. So next slide. So first, we're just going over the background. This is basically the processors that we're mainly dealing with in this presentation, and then the steps we took to run our applications on the ISS. So next slide. So the first processor is the Qualcomm Snapdragon 855 HDK. This is an 8-core ARM system embedded processor. It also has a Adreno 640 GPU, a Qualcomm Hexagon 690 DSP, and a neural processing engine that directly supports convolutional neural networks. And this also runs on Android OS. Next slide. So the Rad 750 is an older processor. It is currently running on MSL and in 2020. And we're going to use this mainly to benchmark our different applications against Snapdragon. Next slide. So the Sabertooth is another benchmarking processor for us. So this is a Leon 4 based CPU, and where this is supposed to be an evolution from the Sphinx processor. Next slide. So this is simply a table just comparing the different aspects of the processors. I will note that the Movidius Myriad X was not mentioned before. That's because there's another presentation done by Emily Dunkel and Leonie Buckley at this conference. It's a pre-recorded presentation that I encourage you to check out, but that will go more in depth on the Movidius and what we're running on it. Next slide. So as for what is actually physically on the ISS, we have a Hewlett-Packard Spaceport Computing 2 package. This is otherwise known as the SBC2 to us. And this is a Linux workstation that runs on an Intel Xeon processor. It has 4 Tesla GPUs, and then we have 2 of these. So over the 2 machines, we have 4 Tesla GPUs, and each runs on a Xeon processor. We have 2 Snapdragon boards up there, and then also 2 Myriad X processors. Next slide. So to run our applications on the ISS, we first test and develop these applications locally. So we have Snapdragon boards here that we're testing them on. Once we believe they're ready for flight, we then send them to a ground test bed that HPE runs, and we test them locally there. That test bed more exactly mirrors what we expect to see on the ISS. Once that is ready, we tell HPE, and they test that on another ground test bed that we don't have access to. And if it passes on that test bed, it is then sent to the ISS and run. The results are taken and then sent back to us. Next slide. So to run our applications, we created a test harness. This test harness can be run on your Mac or any Linux processing, any Linux workstation. So effectively, what this test harness does is it iterates through all the experiments for applications that we're running. And for each experiment, it pushes all of the code or data necessary to the Snapdragon. It then runs the application, pulls the results out, and then wipes the board clean of anything that it just pushed on. It then returns those results so that we can analyze them. So every application we're running is effectively running on the same board. Next slide. So now we're going to go into some deep learning models that we have running on the Snapdragon itself. Next slide. So currently we have 8 deep learning models running on the Snapdragon on the ISS, and we're just going to go over 4 of them, as we have a lot of other applications we're going to go over too. So we're just going to show the range of what we deployed. Next slide. So the first one is the Mars HiRISE deep learning classifier. This does landmark classification. So we're trying to identify Mars surface features using orbital imagery. So we're doing this for autonomous data collection, targeted downloads. And this classifier runs based on the HiRISE instrument on board the Mars Reconnaissance Orbiter. And the model is a transfer learning from AlexNet. Next slide. So when looking at how these performed on the Snapdragon, we run with the classification discrepancy. Now this is a comparison to how well it performs compared to running it on a simple laptop, so a MacBook. And this is a difference in performance. So you'll notice that performance drops when you run with the DSP or NPU. And this is because to run on either of those, we need to quantize the model. So what this means is mapping all the floating point numbers to fixed points. So we have some rounding errors, which causes some overall errors in the classification. As you can tell with this model, that was not very high, and we get a significant performance boost in runtime. Next slide. The second model is the NavCam deep learning for terrain classification. So as the image shows, we are classifying the different types of terrain we see on Mars. So we want to be able to do this for onboard navigation and science interpretation of the Mars terrain. And we are using data from the Mars Curiosity NavCam and using a Deep Lab V3 architecture for image segmentation. And this is developed to support the MSL rover planners. Next slide. So here we see that the quantization actually causes a bit more of an error, but again, we're seeing a significant increase in the runtime. Next slide. So super resolution for spectroscopy is another model. Here we are trying to infer high resolution data from low resolution data. So this would be used for improved rock and mineral identification for onboard data subselection. And so here we're getting 85 band average NG data from 5 band Aster data. We're using a deep Gaussian conditional model. And interesting for this model, we found that the CPU is actually twice as fast as the DSP or AIP, which is interesting. But we believe this is due to the fact that the model is a bit small, and also to do this, it's very single pixeled. Next slide. So looking at previous flights of machine learning classifiers, we see that there's not a lot of deep learning flying in space. Previously, there's been random forest and Bayesian thresholding as a more simpler classifiers being run, and FISAT is an example of a deep learning mission that uses the deep learning for image classification or for cloud identification, so it can throw out cloudy data. Next slide. So now we're going to be looking at the other AI that we're flying on board the ISS. Next slide. So as this shows, we have about 3 general types of other AI algorithms being run. First are general algorithms, then we have instrument processing algorithms, and then we have planning algorithms. Next slide. So before we jump into the algorithms themselves, we just want to quickly go over how we got these algorithms onto the Snapdragon board itself. For the C and C++ algorithms, it was very simple to cross-compile their code for the ARM v8A architecture. The ARM ports are pretty straightforward, and to only run it single-threaded or multi-threaded is pretty simple. Now, to run it on the GPU, DSP, or NPU, that takes a little bit more effort, but is definitely reasonable. And we have some other applications running on Python, which uses the Python for Android library provided by Kivy. And eventually, we wish to benchmark all of these applications on the processors that make sense. Next slide. So the first general algorithm is the fast Fourier transform. So this chart generally shows that we're getting a pretty significant boost in runtime by using the hardware acceleration available to us on the Snapdragon. This can be done just by looking at the runtimes of the GPU for the more complex problems. Next slide. This graph is for a matrix multiplication benchmark. This does an even better job of showing just how well this hardware acceleration keeps runtimes lower as the complexity of these problems increases. Next slide. So the first signal processing application is Europa lander stereo vision. So this application takes a pair of stereo images as shown in the figure, and it turns them into a depth map. Now the images are input at the resolution of 5120 by 3840, and we see the time to create this depth map in 3 different levels of resolution. So we can see how the runtimes drastically decrease as we decrease the resolution of the image. And this application runs on the Snapdragon ARM. Next slide. We were able to compare this to the RAD 750 as a benchmark. Really what we see is that over the 384 by 512 pixel image, we're getting a significant decrease in runtime by using the Snapdragon when compared to the RAD 750. Next slide. So the next signal processing is decision trees. The first one is a thermal anomaly detection. So this is a decision tree logic, which is based on the paper cited there. And it classifies hot and extremely hot pixels using multiple radiance bands. This is run over AVERS NG data, which has 425 bands, and the image is 4500 by 390. And we were able to implement this on the ARM and GPU. Next slide. So we also have a Cryosphere decision tree, which is based off of a different paper. And instead of identifying hot and very hot with the different radiance bands, we're able to identify clouds, water, snow, ice, and land. This is run over a same sized image of AVERS NG data, and both of these are run after another on the CPU, on the ARM and the GPU, and we find that the GPU gives us about half the runtime as the ARM. Next slide. So we also have a random decision forest that we created. This random decision forest runs over planet SkySat data with 4 bands of radiance. We trained this on a 13 image training set. 11 of these were of the Reykjanes volcano in Iceland, and 2 of them were of Kilauea. We then tested this on 4 million pixels from one of the Reykjanes images that was not in the training data set. The random decision forest that we created has 1,300 trees, where 100 trees were created from each image. It has a max depth of 10, and the weights are equalized by class. This runs single threaded on the CPU or the ARM, and it runs in about 10.5 minutes. Next slide. High order wavefront sensing is a Python implementation for the Roman Space Telescope chronograph instrument. Currently, our runtime is a little bit slow. We were able to get it down to 1.8 hours, but we hope to be able to speed it up by utilizing the GPU, multi-threading, and in order to do those things, we need to move it off of Python. Next slide. The synthetic aperture radar is an imaging processing pipeline using UAV from the UAVSAR instrument. This is actually a pipeline, so it has 3 ARM applications and 2 GPU applications. The main one is a row-wise and column-wise 2D fast Fourier transform with filters. Our goal was to get this to be roughly real time, which would be 240 seconds for this image size, and we currently have it down to 217 seconds of runtime on the Snapdragon. We could do this further though, because we're not fully utilizing our GPU. Next slide. Match filters is an application running on AVERS data of the Cuprite site, and it's run over to identify different minerals in the ground based off of the radiance data, the spectral data. So we plan to expand this to 20 minerals. Currently, we are able to identify roughly 3. This runs on the ARM and is single threaded, and we don't really think multi-threading is going to improve this too much due to the heavy IO usage. The image size is listed, and to go through 8 of these images looking for 1 mineral, it takes roughly 850 seconds on the Snapdragon ARM. Next slide. We also ran the match filters over lunar data. Here we are looking for volatile water molecules instead of the minerals from before. So this would be OH, molecular H2O, and H2O ice. Again, identical to the algorithm before. So it is single threaded on the ARM, and its performance mirrors match filters. For the image size we have, it takes roughly 108 seconds. Next slide. Hyperspectral compression was benchmarked on emit data. And currently we only and we were able to benchmark this on the CPU, GPU, and DSP. For going over its performance, we look at the number of samples per second we're able to process. Our goal is to get near real time, which was 23.1 samples per second. And if we look at the GPU, we were able to beat this handedly. Next slide. SMAC is a sequential maximum angle convex cone end member extraction. So effectively, this finds the top 5 end members from the data. These can then be matched up with other minerals that we know, so we can identify minerals from spectral data. Using the image size that we have over AVERS NG data, we have about a 17-second runtime. This application is based off of the paper cited as well. Next slide. The landing vision system is an application to find safe places to land spacecraft based off of images. So this is actually a pipeline with two steps in it. The first one is a core step, which mainly runs a fast Fourier transform. We are able to run this with in about 2.5 seconds over a 1024 by 1024 image. The fine version is a normalized cross correlation, which runs in about 2 seconds over an image of the same size. And this is implemented on the Snapdragon ARM. Next slide. The Ocean Worlds Life Surveyor is a project to autonomously detect signatures of life in water. And this is going to process data and look for outliers that could be life and return these as autonomous data science products for us to analyze. So this is implemented on the ARM of the Snapdragon. We are working on a multi-threaded version, and currently we are running on a data set of 24 images, each 1024 by 1024. And our runtime is a little bit less than 1 second per image, for a total runtime of 22.5 seconds. Next slide. ESPRIT is a method to detect signal interference. We have to take an eigen decomposition of a 20 by 20 matrix to a 100 by 100 matrix. This is something that the power of the Snapdragon actually lets us do a lot faster. Currently, it's single-threaded, implemented in Python on the Snapdragon, and it runs in 20 minutes. Next slide. So we were able to benchmark this against a Leon 3 processor. And once again, here we're showing the added benefits we have of even the single-threaded version, and then even faster multi-threading this application. Next slide. Delay-tolerant networking is another application that we're able to take advantage of the power of the Snapdragon. So this algorithm works by traversing a graph to set up a relay network and find the next node forward. It's done similar to Dijkstra's algorithm to find the best node to forward data. It's implemented in Python, runs single-threaded on the CPU or the ARM, and runs in 35 minutes on the Snapdragon. Next slide. So overall, other planning and scheduling has been flown in space before. However, when we're looking at those different projects, the response time is largely around 10 or more minutes, and we want this to be a lot faster, as will be explained in the next application. So next slide, please. So SMICES pointing planning is an application where we want to actively aim a radar at scientific targets. In this case, the scientific targets are storm clouds. So we have a way to identify storm clouds, and as we fly over, we wish to aim the radar at the most scientifically valuable ones. So in this, we run over a simulated data set of the Caribbean, and we're able to run 8.5 hours of simulation time in only 54 seconds on the Snapdragon ARM by generating an observation list based off of the constraints of the mission. Next slide. So this is about the opposite of the previous application. Here we're trying to take images that avoid the clouds. So 4 algorithms are developed here. There's a greedy search algorithm, and then there's 3 graph search algorithms that increase in complexity from fixed grids to adaptive grids. This application is actually implemented in Rust on the Snapdragon ARM, and the runtimes per image are listed for each of the different applications. We did run this over a 50 image data set with the dimensions listed. Next slide. MXEC is a separately threaded planner and executive. So basically, we give it a task network, and it generates a conflict-free plan and is supposed to monitor the execution of that plan. Next slide. So for our testing, we're only going to deal with the planner side because that is the most computationally expensive. We're only going to do the first generation plan to make it simpler, and we're running this over Europa lander prototype test scenarios. This is running single-threaded on the ARM. Next slide. So here we have a comparison of the runtime that we were able to achieve on the Sabertooth versus the Snapdragon itself. The Intel Xeon is the server processor we said before. So we're seeing a significant increase here against the Sabertooth. Next slide. CLASP is a compressed large-scale activity schedule and planner. It is being used in NISAR, EcoStress, and some other missions. And currently, the goal is to generate an observation schedule based on a scenario constraints for a constellation of satellites to collect scientific data. Next slide. The scenario we have is to generate 2 years of 2-week schedules using EcoStress data. We generate single 2-week schedule to collect our timing metric. Currently, this is single-threaded on the ARM. We're looking into putting this on the GPU as well. Next slide. So overall, we were able to run around 1,400 seconds for this application. Next slide. So Copilot is the ground scheduler for the M2020 project, for the M2020 operations, and it monitors scheduling in wake, sleep and wake and preheats. This is the same scheduling algorithms that M2020 being run on the Snapdragon. Next slide. For our test, we're trying to run 800 sols or 800 planning problems effectively, where we're generating for random variation of 7 base plans. We have a single-threaded and multi-threaded version, and we're going to benchmark against the Xeon processor. Next slide. So overall, we have the single threaded on top and the parallelized one on the bottom. And the biggest takeaway here is that we're able to generate 800 plans in roughly 500 seconds for the multi-threaded one. So that is less than 1 second per plan. Next slide. So moving into future work, we wish to measure some additional computing performance metrics for each of the applications. We want to measure the power, energy consumption, and the RAM footprint. We want to get to more processors, being the Sabertooth, the Rad 750, Jetson Nano, and other processors. And we want to be able to parallelize more of these applications and also use the hardware acceleration available for more of these, and next slide. So here are just an example of some of the additional applications that we are hoping to get onto the Snapdragon. Next slide. So overall, we were able to port machine learning and processing, scheduling, and benchmark applications on the Snapdragon on the ISS. We were able to benchmark these not only in the Snapdragon, but also the Movidius. We have a Linux benchmark, the Sabertooth, the Rad 750, and working on the Jetson Nano. We're working towards collecting more data on each of these applications, and we intend to facilitate future flights with these capabilities and enable better processors. Next slide. So I'd just like to thank everyone who helped us. And then I would also like to point people towards the sister presentation about the Myriad that I mentioned before. Again, this is benchmarking deep learning on the Myriad X processor on board the International Space Station. It's one of the pre-recorded talks, and it's by Emily Dunkel and Leonie Buckley. Next slide. I think that should be it. Thank you.
All right, thank you, Jason. We've got about 5 minutes for some questions. And so I'm going to start going down the list. So first question from Peter Fiddleman. For the Snapdragon on the ISS, did you notice any single event upsets or device resets? Yeah.
So we did have, we ran a GPU test of just pushing a bit through the GPU. We did not find any resets or any memory issues from that. Someone on our team did the math and said we probably need to run it for about a year to find one of those.
Okay. Next question from Anomaly. What GPU API did you use on the Snapdragon?
So we mainly used OpenCL. Yeah, OpenCL.
Okay. Next question. Were you able to determine how much power was consumed for each image inference? And I think this was on some of your earlier slides.
Each image inference, so that would probably, is this for the deep learning or?
I see it was asked at 5:04, sorry, so one of your earlier slides.
One of the early ones. It's possible. If it wasn't in one of the charts, I don't quite have access to it. Expanding to measure the power is something we wish to do more thoroughly. Okay.
And another question from Amelie. Yocto or Ubuntu? I think this was also on your earlier deployment slides.
Oh, I believe it runs on Red Hat.
Red Hat, okay. We've got a few minutes for a few more questions, and we'll give some time for things to filter in. Next question from Leonidas. How did you program the digital signal processor?
The DSP. So the DSP was mainly used for the deep learning, for which we were able to use, the deep learning uses a package called SMPE to run, I believe we used cafe models. So then you can simply set a variable in there and it uses the DSP instead of the, yeah, basically.
Okay. Give another minute or two for some more questions to filter in. All right, Jason, thank you so much. Awesome. One just came in. Are you planning to open source any of the benchmark applications?
Source them. I think someone before that might take some approval. So I'm unsure.
Okay. All right. Thank you so much, Jason. Next up on our agenda is a break, and so I think we'll go into that. Thank you again.
Thanks so much.